Welcome to the Problemas channel, Season 2, Episode 12, the episode in which we will discuss the solution of the mathematics problem S2M14. But before that, we would like to make our traditional and friendly reminder that if you are joining our channel mid-season, then it is always a good idea to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problemas Channel How To, and watch that episode in its entirety and follow all the instructions given in that episode, because in that episode we explain and motivate everything that we do on this channel. Why I have titled this episode Not Blind Mathematical Justice will become apparent in a few minutes, but as a refresher, in the mathematics problem S2M14 we're given a set of 12 visually indistinguishable points, and we're told that out of these 12 points, 11 are genuine, fair, and not fake coins, and precisely one coin is fake, not genuine, and not fair, but it is not known whether that one coin weighs detectably more than a genuine coin, and it is not known whether this one fake coin weighs detectably less than a genuine coin, and that is the intellectual challenge in this specific problem. Using one set of fully functional and fair pen scales in no more than 3 weighings, we are to determine with absolute certainty the following 2 units of information. We are to recover the identity of the fake coin with absolute certainty, and we are to recover the weight quality of that fake coin with absolute certainty. That is, with absolute certainty, we are to determine if the fake coin weighs more or is heavier than a genuine coin, or we are to determine with absolute certainty that the fake coin weighs less or is lighter than a genuine coin, and we again are to do all of this recovery of the required information with absolute certainty. To the best of my knowledge, this problem was first published in the West in 1945, and the author of that problem is the famous theoretical physicist Freeman Dyson. And again, to the best of our knowledge, but by all means feel free to verify our information, about 1 year later and independently from Freeman Dyson, that same problem was published in 1946 in the publication called American Mathematical Monthly in the issue number 3 in March. And in that issue, that same problem appeared under the number E for elementary 712. And again, to the best of our knowledge, the problem was put together independently of Freeman Dyson by the gentleman called Donald Ives. And about 8 months later, in 1947, in the same publication, American Mathematical Monthly, in the issue number 1 in January, 2 types of solutions, adaptive and non-adaptive, were published. And unfortunately, I have to say that after I have read both of these solutions, I thought to myself that, gee, with all due respect, it is more exciting to watch grass grow and paint dry than to read these paragraphs, number one. Number two, there is absolutely no motivation of any kind as to how can anyone approach generating that solution. And number three, there is no complete enumeration of all distinct adaptive solutions of this problem, and that is precisely what we will do in this episode. In this episode, we'll provide a plenty of motivation as to how the search for a solution, for an adaptive solution of this problem, can unfold. We will also provide all or enumerate all 13 distinct solutions of this problem in the case when in the first weighing the pans do not balance or tip over, and we also provide the 2 distinct solutions for this problem that come out in the case when on the first weighing the pans do balance. And at the end of this episode, using the grown-up mathematical notion of mathematical entropy, we will show how, using straightforward numerical computations, all the observations that we make in our episode can be actually proven numerically. But before we do that, let us try to understand how does the how does the problem-solving approach that we're studying right now, the space-time problem-solving approach, dovetail into the process of searching for an adaptive solution of this problem. Across all the problem-solving approaches that we will be studying on this channel, the space-time problem-solving approach is perhaps the least complicated or the least complex one, but at the same time it shows that for something to be useful and reasonably powerful, that something doesn't have to be overly complicated at all, and sometimes simple does it. That is, in my problem-solving experience, I have noticed that in certain problems, even in mathematics, there exists a very pronounced spatial and temporal interaction between the events and or objects in such problems. And in a somewhat coarse manner, when it comes to the ways in which the space and time can be paired in these problems, there exists only 4 interesting such pairings, and I have captured these pairings in the table over here, and that shows over here that in certain problems, the interaction between the main components or certain events in such problems can happen at same time in same space, at the same time in different space, at different time in the same space, and at different times in different spaces. For example, to give a somewhat loose but fairly technical and fairly representative example of what the space and time mean. From the perspective of the space-time problem-solving approach, time is pretty much what it is, but space is somewhat loose and it can be what it needs to be in the context of a given problem. For example, let's say we want to have an example of something that happens at the same time at the same space. Well, for the same space, we can, for example, take a campus of a college and then at the same time, let's say at 9 o'clock in the morning, the same things, or for example, different lectures can happen on the campus of that college if we take the campus as one whole unit, and that one whole unit represents the space, thus same time, same space example. If, for example, we decide to get a little bit more precise or zoom in on the campus of a college, then for example of events that can happen at the same time in different space, we can, for example, distinguish, let's say, 2 lecture halls, lecture hall A and lecture hall B. And then at 9 o'clock in the lecture hall A, there goes on a lecture on mathematics, and at 9 o'clock at the same time, but in a different space, in the lecture hall B, there goes on a lecture on physics, for example. For an example of things that can happen at different time in the same space, we can take again the same lecture halls and our favorite subjects. For example, at 9 o'clock in the morning in the lecture hall A, there is a lecture on mathematics, and at different time, let's say 12 o'clock in the afternoon, in the same lecture hall or in the same space, there is a lecture on physics. And lastly, for an example of events that can happen at different time and at different space, we can again, for example, look at a lecture on mathematics that takes place at 9 o'clock in the lecture hall A, and a lecture, let's say, on physics that takes place at 12 o'clock in the lecture hall B, thus giving an example of different times and different spaces. However, it should be understood that there are certain limitations to the scope and the overall scenarios of problems that in which the space-time problem-solving approach can be applied, and this limitation is mostly comes down to classical physics or the situations when the relevant velocities are much smaller than the speed of light in vacuum and in the presence of small enough masses. And that is why, because the bone of contention in this case is this specific square, same time, different space, because in general, under the mathematical apparatus of special theory of relativity, it is basically fundamentally not possible to distinguish if two events that took place in two different points in space occurred at the same time or not. In other words, under the mathematical model of special theory of relativity, the notion of simultaneity loses its classical interpretation. There exists one somewhat exotic condition even in the special theory of relativity, and that is when the frame of reference of interest is moving strictly perpendicularly or orthogonally to the straight line that connects the two distinct points in space. Now that we understand a little bit what does the pairing of space and time may mean, overall, the space-time problem-solving approach basically suggests that when we come across such a problem, we simply try all these possible pairings, regardless of we think they're useful or not, but we should just try them all, see if any one of such pairings can actually help us solve the problem. And sometimes, and this situation speaks probably more about the psychology of solving problems, because quite often in the adrenaline rush to solve this or that technical problem, we somehow, for all sorts of fabulous reasons, fail to notice a straightforward solution that is hiding in plain sight and sitting literally right in front of us. And with that explanation of how the space-time problem-solving approach works, let us see how it can be helpful in the process of searching for a solution of the problem S2E14 with the fake point detection problem. Coming back to our problem, recall that in Season 1, Episode 2, we explained how to practice mathematics correctly, and the first step of that practice was a deep and true understanding of the problem statement. Do we understand what is required of us in this problem? By the looks of it, the terminology in this problem is very straightforward. We understand each and every word, and we understand what needs to be done. But do we understand what is the expected response? In other words, as a response to the challenge, find and describe a way to detect the two bits of information with absolute certainty. What are we expected to produce? What is the form of that response? Well, fundamentally, we see that we given only one set of functioning and fair pen scales as a device, and that is the only device that we're given. And the only other material that we're given in this problem are the 12 coins themselves. Consequently, it looks like the expected response for this problem is a finite description of 3 or no more than 3 distributions of coins over the panes in this problem. But now let's step back a little bit and ask ourselves, fundamentally, what is a distribution of coins over the panes? And this is precisely where the space-time problem-solving approach comes in, because it has here we have a good interpretation for both times and spaces. That is, the two straightforward candidates for spaces are the left pen and the right pen. Consequently, in this problem, we will have one space called the left pen and another space called the right pen. However, when we begin attacking this problem and when we will begin solving a similar problem with much smaller number of coins, we will quickly realize that stepping, for example, from 2 coins to 3 coins already shows that these two spaces, the space of the left pen and the space of the right pen, is simply not enough, and we need one more space in this problem, and the spirit of this space says that it should be not on the left pen and not on the right pen. And collectively, for demonstration purposes, we'll refer to that third space as the table. And in other words, the table will be basically our abstract device on which we will keep all the coins that do not participate in any given weighing explicitly. I mean, obviously these coins participate in the weighing implicitly, but on the table we will keep all the coins which are not on the left pen and which are not on the right pen. Consequently, in this problem, from the space-time problem solving approach, we have three spaces to deal with: the left pen space, the right pen space, and the table space. And as a expected response to the challenge of find and describe a way, we need to produce no more than three sets of distributions of the coins over same or certain spaces and at the same time. And when it comes to the same space, same time situation depicted in the table on your right, we have what? We have precisely one pen. That is, all the coins that go onto, let's say, left pen will be sitting on that pen at the same time, at the same space when the measurement is performed. Likewise, all the coins that will be placed on the right pen will be located at the same time, at the same space of the right pen, and likewise, all the coins that will be sitting at the time of this weighing on the table also will be sitting at the same time in the same space, and each one of these individual spaces, the left pen, the right pen, and the table, represent exactly the pairing of the main objects or the main components of this problem that corresponds to this square. Same time, same space. Likewise, the same time different spaces pairing of the main components of this problem will be represented by the weighing itself when we finalize our distribution of coins over the respective spaces and say that this setup of coins that unfolds at the same time across three different spaces represents precisely the measurement. And what does the time in this problem represent from the space-time problem solving approach? Well, in this case, the same time is precisely the time during which this specific weighing unfolds. Consequently, summarizing, as an expected response in this problem, we are supposed to produce no more than three same time, same space, and same time, different space distributions of or pairings of the main components of this problem, and that is the coins, the pens, and implicitly the table. And it turns out that when it comes to this specific pairings of coins, pens, and the table in this problem, there exist two distinct solutions that can be generated: an adaptive solution and a non-adaptive solution. A solution of a fake coin detection problem is called adaptive if in such a solution the result of the current weighing does affect the distribution of coins over the pans and over the table in the next weighing. Every adaptive solution of a fake coin detection problem has two interesting and characteristic properties. One, in each adaptive solution of a fake coin detection problem, it may so happen that some coins will sit out the entire weighing experiment on the table and will not be put on the pans altogether at any time. Two, as a result of each weighing in each adaptive solution of a fake coin detection problem, we eliminate the coins from the suspect pool and promote them into genuine or so-called control coins. In contrast, a solution of a fake coin detection problem is called non-adaptive if in such a solution the result of the current weighing does not affect the distribution of coins over the pans and over the table for the next weighing. A characteristic feature or a characteristic property of each and every non-adaptive solution of a fake coin detection problem is the fact that in such a solution all the coins that are given in a specific problem are eventually or at some point put on the pans, or in plain English, a characteristic feature of each and every non-adaptive solution of a fake coin detection problem is the fact that in such a solution, every coin is marshaled through the pans at some point, and unlike in a adaptive solution of a fake coin detection problem, no single coin in a non-adaptive solution of a fake coin detection problem is ever left on the table. Also, alternatively, in plain English, each and every non-adaptive solution of a fake coin detection problem is planned or described or defined ahead of time before even the first weighing of that solution begins. In other words, if, for example, we are the authors of a non-adaptive solution of a fake coin detection problem, then we can write down that solution in its entirety on a piece of paper, give it to someone who has absolutely no idea what is going on. We, as authors of that solution, can simply walk out of the room, let the person follow the instructions, follow the recipe, so to speak, that is written on the piece of paper. And once that person carried out all the steps that were written on the piece of paper, we can walk back into the room, look at the result of the experiment, and announce to the world, this coin is fake and heavy, or this coin is fake and light. In this episode, we will develop an adaptive solution of a fake coin detection problem, and in the following episode, we will look at an introductory level solution that is non-adaptive. Before we deep dive into a process of searching for a solution of the mathematics problem S2E12, I would like to make one remark about a specific quality of this problem. That is, it seems that each and every person starting from the age of, let's say, 12 to 13 and above will be able to understand each and every word in this problem, precisely because the statement of this problem is on a strict diet from highbrow and highly specific mathematical jargon. That is, in the statement of this problem, there are no quadratic residues, there are no nested chains of commutator subgroups of a group, there are no contour integrals or nonlinear differential equations in partial derivatives. Yet, out of the statistical majority of the people who are given this problem and who can and will understand each and every word in it, the majority again of these people will not be able to solve this problem, unfortunately. And in all fairness, this problem is quite complicated. That's why it should be given an asterisk over here. And it is interesting, why is that? In other words, on the one hand, when we think, gee, why would anyone in their sane mind will be interested in studying, let's say, chains of nested commutator subgroups of a group? And what is the commutator subgroup of a group? Well, it takes students on average several years of a concentrated effort to finally be able to decipher and understand that, for example, the commutator subgroup of a group is the unique smallest subgroup of the parent group, the quotient group of the parent group with respect to which is the commutative subgroup. Also, it so happens that under favorable conditions, let's say the commutator subgroup of the parent group may be, intuitively speaking, be slightly smaller. And consequently, because every subgroup is a group itself, we can apply the notion of the commutator subgroup to the subgroup and so on. And if in a finite number of such nestings, this chain of the commutator subgroups of the parent group terminates with the trivial group, then it turns out that the parent group itself is solvable. Also, it so happens that in the family of the so-called finite alternating groups, or the groups of even permutations, it so happens that starting with finite alternating group A5, no such group is solvable. In other words, the finite alternating group A5 is the first unsolvable group, and all the consequent groups are not solvable as well. Also, amazingly enough, these finite alternating groups have something to do with the roots of polynomial equations, and through the relatively highbrow mathematics, it can be shown that if the corresponding finite alternating group is not solvable, then for the corresponding polynomial equation, there simply does not exist a closed form formula for the roots of that polynomial equation, which is a finite combination of finite number of nestings of radicals combined with the traditional arithmetic operations of addition, subtraction, multiplication, and division. Consequently, we now know that the polynomial equations of order 1, 2, 3, and 4 do admit the existence of a closed form formula in which, through a finite number of extractions of roots and addition, subtraction, multiplications, and division, such roots can be expressed. And in general, we now know, precisely because the finite alternating group A5 is not solvable, a general quintic polynomial equation, or polynomial equation of order 5, does not admit the existence of a formula for its roots, again, as a finite expression that contains only radicals, addition, subtraction, multiplications, and division. Consequently, if anyone, again, in general, is asked to solve a problem that has anything to do with these commutator subgroups, it is evident that most people will not be able to do it, simply because they will not understand a single word in such a problem. In contrast, in our problem S2M14, there are no nested chains or derived series of commutator subgroups. The language in this problem is very, very plain, very, very straightforward. All we have to do is understand the notion of 12 for the number of coins, 2 for the number of pence, 3 for the number of weighings, and about the only other more or less advanced concept that we need to understand in order to solve the problem is what is called in grown-up mathematics the order relation, or we need to be able to understand that a comparison of two entities can happen, and the result of this comparison could be less than, equal to, or greater than. So what gives? The absence of highbrow, highly specialized mathematical jargon on the one hand, seems to suggest that yes, anyone should be able to solve this problem because again, the language of this problem is very straightforward. Yet that is not the case. What does this phenomenon tell us? In my humble opinion, this phenomenon tells us that for the essence of what mathematics is to manifest itself, that essence does not have to be wrapped into the highbrow, highly specialized mathematical language. Sometimes for the essence of what is mathematics to manifest itself, that essence can be wrapped into quite straightforward and, let's say, the proverbial middle school level language. And as we develop the solution of the problem S2 and 14, we also in parallel and hopefully will gain a slightly deeper understanding of what mathematics is. Precisely because this problem is very difficult, and if you practice mathematics correctly as we described that process in season 1 episode 2, chances are that you were not able to solve this problem on your own and correctly. And at that point, among all the people who try to do that, there will be a branching point. Some number of people will give up and walk away from the problem, and some number of people will dig in their heels and continue the academic fight. And the question now is exactly how do you fight this academic fight? Well, one way to proceed here is to follow the advice of Gregory Poya from his immortal book, How to Solve It. And that advice amounts to another problem-solving approach that we will study later on, and I'll put a couple of episodes dedicated precisely to that approach. But for now, relevant to our problem, one way to proceed is as follows. As Gregory Poya says that if you cannot solve the current difficult problem, let's say we represent the current difficult problem with a point like so, then there exists a simpler related problem that you can or cannot solve. So here we're suggested to find that problem and try to solve that problem. However, if we cannot solve that simpler related problem, then recursively we apply the same idea to that simpler related problem as well, and we state that if it is this problem that we cannot solve, then there exists a simpler related problem that you can or cannot solve. We'll represent that problem with another dot right here. And we can go on like this for a while. If it is this simpler related problem that you cannot solve, then there exists another yet simpler related problem which you can or cannot solve. And that chain apparently can run for a while, but it must necessarily be finite. So let us say in this chain of simplifications, we hit the so-called rock bottom. And what is a rock bottom in this chain? The rock bottom in this chain is a simplest related problem that can possibly exist in the specific scenario right here. And if it so happens that you cannot solve even this simplest rock bottom problem, then there is absolutely no hope, there is no way, and there is no chance that you will be able to solve the original very difficult problem. And here you need to seek an advice from somewhere else. But let us say you were able to solve this problem on your own, and we will reflect this with an arrow like so. This arrow, in other words, over here represents your ability to solve the simplest related problem in this chain of reductions. Then, the way this miniature theory works is that during the solution of the simplest problem, you likely develop certain tactical and or theoretical insights which you are suggested to take into the solution of the previous problem that was simpler on the way down and now becomes slightly more difficult on the way up. Let's say you came over here, it's basically the same problem, but here you know how to solve the simplest related problem. And again, using the insights, both tactical and theoretical, that you developed during the solution of the simplest problem, you should try to solve the next simple problem. And let's say again, you were able to do it. And the way this little theory works is that, again, you are suggested to take the insights developed in this problem during the solution of this problem and this problem, and take it into the attempt to solve the next, slightly more difficult problem, and the next, and so on, until you dig your way out of the hole and are able to solve the original very difficult problem. Consequently, here with this 12 coin problem, chances are, again, unfortunately, that you were not able to solve it. And again, you either gave up or you did not. And if you did not give up, then it is highly likely that you realized, the simplest related problem that has something to do with this overall scenario has to do with very small number of coins. Consequently, this is what we shall do, and we will look at 0, 1, 2, 3, and small number of coins. In real time, different people who have failed to solve this problem correctly and on their own right away may proceed in different ways. And for example, some number of these people will or may try to carefully roll down the number of coins in this problem from 12 to 11, from 11 to 10, 9, 8, 7, 6, 5, and so on. And that is a perfectly fine thing to do. Here, for demonstration purposes, we'll cut to the chase, and in the previously explained chain of reductions, we'll jump right away to the rock bottom simplest related problems, and we'll start looking at the problems of 0, 1, 2, 3, and so on in number of coins. In combinatorial analysis, the number 0 is actually quite meaningful and interesting because 0 items can be arranged in a certain configuration in precisely one way, but in our fake coin detection problem, 0 coins doesn't really make much sense and it's not interesting, so we discard the 0 coins case and we begin our investigation and the search for a solution of this problem with the case of 1 coin as shown over here. Now, the spirit of this problem and a large number of related problems says that this 1 coin precisely must be fake because, again, in a large group of such problems, it is 1 coin that is fake, and we need to find either its identity or an identity and its weight quality. And in this case, we're given n coins, n equals 1, so 1 coin must be fake. Thus, in 0 weighings, we right away know the identity of the coin. This coin is fake. However, now we realize that at this point, our research and our analysis will branch depending on whether the weight quality of the fake coin is known ahead of time or the weight quality of the fake coin is not known ahead of time. Let us assume that as our first case for analysis, the weight quality of the fake coin is known ahead of time. And here, for the duration of this episode and a few next ones, let's say that if the fake coin weighs more than a genuine coin, then we will say that the fake coin is heavier than a genuine coin, and we'll designate these coins with the letter H if we know the weight quality of such a coin at some point. And if the fake coin weighs less than a genuine coin, then we will say that the fake coin is lighter than a genuine coin, and we will designate such coins with the letter L. As such, let us assume for our first attempt that the quality of the fake coin is known ahead of time. It's either heavy or light, and in that case, again, it becomes evident quite quickly without much intellectual effort that even in this case, the problem is solvable with precisely 0 weighings. We know right away and upfront that this coin here is fake and heavy. If it is known ahead of time that the fake coins are heavier than the genuine coins, or this coin is fake and light if it is known ahead of time that the fake coin is lighter than a genuine coin. However, if it is not known ahead of time whether the fake coin is heavier or lighter, then we realize that in no amount of weighings this problem is solvable, because in general we cannot even execute any meaningful weighing since we do not have any other coins to balance our fake coin or fake suspect with. And at this point, we move on to the next case where we need at least two coins to deal with. In the previous segment, we saw that if the weight quality of the fake coin is not known ahead of time, then it becomes impossible to solve the one coin problem altogether, because simply we cannot execute any meaningful weighings at all. And in that case, we need at least one extra coin, and this brings us to the two coin case. Recall that in my previous explanation of how the process of reducing the current difficult problem to the simplest one works, we are advised to take the meaningful and interesting technical and or theoretical finds that we generated while solving the simplest problem into the attempt to solve the next more difficult problem. What was such technical insight that we gained from the analysis of the one coin case? Such interesting and fruitful technical insight was the fact that the quality of the solution of a fake coin detection problem depends heavily on the ahead of time knowledge of the weight quality of the fake coin. If such a weight quality is known ahead of time, then it is possible that a solution of the problem is more straightforward than a solution of a problem when the weight quality of the fake coin is not known ahead of time. Hence, in order to develop the feel for what is going on with two coins, we first assume that the weight quality of the fake coin in the two coin problem is known ahead of time, and we'll begin our analysis with the case when the fake coin is heavy. Since we know the weight quality of the fake coin already, we remember from the previous segment, we will designate these coins, the suspect coins, with the letter uppercase H. And because we're given two such coins, we will designate these coins with H sub 1 and H sub 2. And again, because we have only two coins and only two pens, it doesn't really matter which coin goes into which pen. For demonstration purposes, let's say we put the heavy suspect H1 on the left pen and we weigh it. I'll designate the process of weighing or balancing the coins against each other with this less than or equal to sign, like so. We weigh it against the coin H sub 2. What are the possible outcomes of this experiment? Here again, notice that if we try to solve this problem more or less systematically, then again, we have no choice but to, let's say, again, for demonstration purposes, discover the theory of graphs, because in order to visually depict the various outcomes of this problem, we will draw figures that will essentially be graphs in general and trees in particular. Here again, we will note that if two coins are weighed against each other and it is known that precisely one coin is fake, then we can have only two outcomes. Either the pen, let's say with the coin H1, goes down, and then the pen that contains the coin H2 goes up, or conversely, the pen that contains the coin H2 goes down, and the pen that contains the coin H1 will go up. This physical directions, down and up, can be depicted again in a number of different ways, in which direction of motion of a pen from the pen scales as a result of an experiment is arbitrary. You can do it in a different way. I will do it in this specific way. And again, this is just my preference, because from our everyday experience, it seems only natural to depict the result of the weighing with the downward edge or with the downward line, that, for example, the left, in this case, pen went down, which also means at the same time the right pen went up. So in this case, when the left pen that contains the heavy suspect H1 went down, what does that mean? Well, in this case, it means only one thing, is that the fake coin is H1. In other words, we know the identity of the fake coin, and because the weight quality is known ahead of time, this is it. So we write down H1 is the outcome, is the fake coin. Also, another outcome of this weighing could be that the pen that contains the coin H2 went down. In this case, what does that mean? Well, that means that the fake coin is H2, again, simply in a way by contradiction, because the heavy coin cannot go up, and here the pen with the coin named H1 went up. And because we're given precisely two coins, of which one is precisely fake, then it is not possible to depict the balance between the two pens. And in this case, H2 is it, H2 is the fake coin. The situation when the weight quality of the fake coin is known ahead of time and that weight quality is light, then the analysis is quite simple. Let's depict it below, for example. Again, if we put coin named L1, let's say, on the left pen, and we put the coin named L2 on the right pen, and again, this choice is arbitrary. You can swap these coins with respect to the pens anytime, all day long. But what are the outcomes of this single weighing then? Well, again, let's say the left pen, the pen that contains the coin L1, went down. What does that mean? What kind of useful information can we extract from this result of the experiment? Well, if the suspect is light and it went down, then it doesn't make sense if this coin is fake, because again, in uniform Earth gravity under normal conditions, the light coin simply, or the suspect coin that is lighter than genuine, cannot go down. Here, that means that the pen that contains the coin L2 went up. This coin is fake, so consequently we write down L2 is the fake coin, L2. And another outcome that is possible in this case is when the right pen goes down, the pen that contains the coin L2, and again, a suspect that is lighter than a genuine coin cannot go down. That doesn't make sense. That means that as a result of this experiment, the coin L1 in the left pen went up, and that coin must be the fake coin. And here we see that in the two coin case, when the quality of the fake coin is known ahead of time, then this problem is solvable in precisely one experiment or in one weighing. Now, let us analyze the case when we still have two coins. Still, one coin must be fake, but the weight quality of the fake coin is not known ahead of time. Well, in that case, we lose the luxury of designating our coins as either H or L, because we do not know whether the fake coin is heavier or lighter than the original. And what can we do in this case? Well, in this case, we have only one choice. Let's say we designate one coin as X, the other coin is designated as Y. We put, again, let's say for demonstration purposes, the coin X on the left pen, the coin named Y on the right pen. You can do it in a different way. Be my guest all day long, but here for demonstration purposes, that is what we do. And again, how many outcomes of this weighing are possible? Very well, because we have precisely two coins, precisely one is fake, only two outcomes is possible. Either the left pen, the pen that contains the coin named X, goes down, or the right pen that contains the Y coin goes down. In this case, it may seem that this case is straightforward, but amazingly enough, unfortunately, some students cannot do the right thing over here and make a correct conclusion. What does the outcome when the left pen went down in this case mean? What are the possible scenarios here? Well, precisely because the weight quality of the fake coin is not known ahead of time, each such coin can be either heavy or light. The coin X can be heavy or light, and the coin Y can be heavy or light. Let's say the left pen in this case, the pen that contains the coin named X, went down. What does it mean? Let's draw a little picture over here. The coin X went down and the coin Y went up like so. What conclusions can we draw from this experiment? Well, let's say the coin X, we assume for a moment the coin X is a genuine coin. Well, then the Y, the coin named Y, that went up must be fake, and it must be light in its quality. So we record this result as coin Y with the superscript L. The coin Y is the light suspect. Conversely, let's say the coin Y is a genuine coin, then what can be said about the weight quality of the coin named X? Precisely because the Y coin is genuine, that means that the coin named X is a heavy suspect, and we write down this outcome as X and heavy, like so, and we have two possible outcomes in this case, and we understand carefully why this is so. Likewise, we analyze the case when the right pane, or the pane that contains the coin named Y, went down. What does that mean? Let's draw a helpful picture. The coin named X in the left pen went up. The coin named Y in the right pen went down. Again, how do we analyze this case? Assume that, for example, the coin X is a genuine coin. Then the only outcome here is when the coin named Y is a heavy suspect. We captured the case with the notation Y superscript H. So the coin Y is fake and heavy. That's one possible outcome. What is the other outcome? Well, let's assume that the coin named Y is genuine. What does that mean? Well, that means that the fake coin X went up, and that means that that coin is light. So another outcome is the coin named X is light. And these are the only two outcomes, and these are the possibilities for the weight qualities of the suspects. Now let us think about this together. If we execute one weighing and observe this result, can we solve this problem with one weighing? Well, the answer over here should be evident, and that answer is no, because here, in order to resolve the question of the identity and of the weight quality of the fake coin with absolute certainty, which is what we're required to do in our problem S2E14, we need to generate how many? 4 units of information. 1, 2, 3, 4. 4 distinct units of information, because in our case, the coin X can be heavy, the coin X can be light, the coin Y can be heavy, and the coin Y can be light. And now comes a very important and very clever and enlightening question. How many units of information can be produced with a single weighing on the pen scales? Well, even with this experiment, even though we have only 2 coins, we realize that theoretically a single weighing on a fair and properly functioning pen scales, they're possible no more than 3 outcomes. That is, either the left pen goes down, let's write it down over here, the outcome 1, the left pen goes down, which means that the right pen goes up. Or the second case, the pen's balance, that's the second outcome, the pen's balance. And the third outcome is, again, in terms of, for example, the left pen. The left pen goes up. Left pen goes up, in which case the right pen goes down. And no more other outcomes are possible. Now, that doesn't mean that in a specific case, under specific conditions, all three may be realizable. It may so happen, for example, as in our case, that the balancing outcome is not possible due to the nature of this specific scenario. But theoretically, a single weighing on a properly functioning fair set of pen scales cannot produce more than 3 units of information. And if we now think ahead a little bit, so let's write this down. With one weighing, we cannot produce more than 3 units of information. But let's say theoretically we executed one weighing. We accounted for all 3 possible outcomes. Left pen goes down, the pen's balance. The left pen goes up. And then we executed the second weighing. What can be said in that case? Well, each outcome over here will account for another scenario. And in that scenario, we recursively apply the same idea. We shuffle the coins in some way, put them on the pans, put some coins on the table. We execute the weighing again. And how many units of information can be produced in this case? Well, for each one of these outcomes, we also have another 3. 3 plus 3 plus 3 comes out to 9. So we figure that after 2 weighings, we cannot produce more than 3 square units of information, or 3 times 3. Here will be 1. And if for each of these 9 outcomes, we concoct some sort of distribution of coins across the pens and the table, we execute the third consecutive weighing, then what is the maximum amount of information that we can extract from 3 consecutive weighings then? Well, by the same reasoning, we think that after 3 consecutive weighings, we will generate no more than 3 to the third, or in this case 27, 3 times 3 times 3 weighings. 27, 3 times 3 times 3 units of information. And in general, if we conduct k consecutive weighings on a properly functioning fair set of pen scales, we will be able to produce no more than 3 to the kth power units of information, where k varies as 1, 2, 3, 4, and so on, which is again a notation for a whole positive number. Consequently, from this analysis, we see that in one weighing, we cannot produce more than 3 units of information. More than 3 units of information. But in this case, of 2 coins with 1 fake and of unknown weight quality, how many units of information we need to produce? Well, we need to produce 4 units of information. And because 4 is strictly larger than 3, it follows that the 2-coin problem in its most general case is simply not solvable in one weighing. And now we realize that no matter how we shuffle these 2 suspects, we will not be able to extract more information from this scenario, and we will always be stuck with the demand to produce 4 distinct units of information, but we can only produce 3, and we realize that in the 2-coin case, in its most general case, the problem is not solvable at all. And in order to solve the problem, or we think that in order to solve the problem, we need to move on from 2 coins to at least 3 coins. With the 3-coin problem, the real fun begins. Recall that in Season 1, Episode 2, we explained how to practice mathematics correctly, and we noticed that for some number of people who have not been taught mathematics properly, these people will have an urge to watch the solutions that we present on this channel in each specific episode in its entirety. And we also suggested to resist that urge and only watch the minimum viable amount of information. And the moment you realize, aha, now I see where things are going, we suggested that you pause our video, walk away from the computer, and try to solve the specific problem on your own completely all the way to the end. What we are doing right here in this segment is actually a hint and such a checkpoint, if you will. So we suggest that the moment you understand what is going on, you put this video on pause, walk away, and try to solve the problem completely on your own all the way to the end. And also, as a small hint, what we are doing here and now in this segment has a well-dedicated name, and that name has to do with something that we studied not so long ago. In any case, with the 3-coin problem, based on the analysis of the previous simpler related problems, we know that we have 2 cases to consider, or we know that we're staring at a branch point in our analysis. That is, we can consider the case when the weight quality of the suspect or of the fake coin is known ahead of time, and when the weight quality of the suspect coin is not known ahead of time. We begin our analysis with the case when the weight quality of the fake coin is known ahead of time. Let us assume for now that it is known ahead of time that the fake coin weighs more than the genuine coin. We know that we refer to these coins as heavy suspects, and we designate them with the letters H1, H2, and H3. Here, the question comes up: if all the coins in a given set and in a given problem are visually indistinguishable, then how do we distinguish them and how we give them names? This is actually a good question, and here again we use the wonderful fact that mathematics is an abstraction from reality. We claim that we use the so-called mathematical ink in order to distinguish our visually indistinguishable coins, and that means that the mathematical ink is a massless ink which does not alter the mass characteristic of each coin in any way at all. As such, when we're given 3 heavy suspects, then we begin solving this problem as follows. We shake all 3 coins real well, then we pick the first coin at random, and we put that coin on a randomly chosen pen, left or right, doesn't matter. Then we pick the second coin again at random, but this time we put it on the remaining free and available pen that does not have a coin in it. And lastly, the third coin automatically goes onto the table as depicted over here. And again, for demonstration purposes, let us agree that our distribution of the names of the coins over the pens is as follows. The coin named H1 goes on the left pen, the coin named H2 goes onto the right pen, and the coin named H3 sits on the table. From the analysis of the previous simpler related problem or the 2-coin problem, we know that these 2 are the outcomes that are possible. But because we do have the third coin, now is it possible that the pans with the coins H1 and H2 in them balance? The answer is yes, of course. It is possible that the pans in this case will balance. We will depict that outcome with a straight line that goes down, meaning that neither pen tipped over as a result of this measurement. And can we state with absolute certainty the identity of the fake coin? Well, yes, of course, because the pens on which the coins H1 and H2 balance, it follows with absolute certainty that there is only one choice for the identity of the fake coin, and that fake coin is H3, and we know in this case that the fake coin is this one, and it is heavy. And notice that at the bottom of our, technically in general, this is called a graph in the theory of graphs, and more specifically, this is actually called a tree. And later on, we'll see, when we will see more examples, this will be a tertiary tree. And at the bottom over here with the so-called leaf nodes, what we have is all three possible outcomes for the solution of the three-coin problem when the weight quality of the fake coin is known ahead of time and that quality is heavy. The situation when we're given three visually indistinguishable coins, of which precisely one is fake, but it is known ahead of time that the fake coin weighs detectably less than the genuine coin, we refer to this coin, fake coin, as light. Consequently, we use massless mathematical ink to name all our coins as L1, L2, and L3. We follow the same procedure. We shake the three coins real well. We pick the first one at random. We put that random first coin on any randomly chosen pen. We pick the second coin at random. We put that coin on the remaining free, not occupied pen. And the third coin automatically sits on the table. And again, for demonstration purposes, let us assume that the distribution of the coins over the pens is as follows. The coin named L1, the light suspect 1, goes on the left pen. The coin named L2 goes onto the right pen, and the coin named L3 sits on the table. From the analysis of the previous two coin case, we know that these are the possible outcomes. We already marked them over here, but because now we have three coins, can the pens in this weighing balance? The answer is yes, of course. If the suspects L1 and L2 turn out to be genuine coins, then we know with absolute certainty the identity of the fake coin, and that coin must be L3 that sits on the table. We depict that result with a straight line down, depicting that neither pen tipped over, and in this case, the identity of the fake coin is L3. And again, technically, if we were to get pedantic about it, then these three leaf nodes depict all three possible outcomes of this problem when the weight quality of the fake coin is known ahead of time and it is less and the fake coin is lighter than the genuine coin. Before we move on to the case when the weight quality of the fake coin is not known ahead of time, observe a certain symmetry between the solutions of the heavy fake coin and light fake coin problems. Note that, for example, if we have one such solution, for example, let's say we know the solution for the heavy fake coin, then from that solution alone, we can mechanically obtain a solution of the problem when the fake coin is light. And that mechanical process amounts to uniform replacement of all the letters H with the letters L. And here at the bottom, we just need to swap these two nodes around with respect to the central node L3. That is, the coin named H1 becomes the coin named L1. The coin named H2 becomes the coin named L2. Here, the coin L1 becomes H1. Here, the coin named, H1 becomes L1, and we need to swap these guys around. But the coin that was named H3 now becomes the coin L3, and voila, we have our solution. And conversely, if we know the solution of the problem when the fake coin is light, then we can obtain the solution of the problem when the fake coin is heavy by, again, uniform mechanical replacement of the letters L everywhere in this solution, and then the swap of the right and the left leaf nodes over here with respect to the vertical one. Very well. Now let's discuss the situation when the weight quality of the fake coin is not known. In that case, we lose the luxury of naming our coins as H or L. We have to name them in the most generic way, and we name them as X, Y, and Z. And for the initial or first weighing, we perform the same algorithm as the one we described before. We shake all three coins real well. We pick the first coin at random. We put that randomly chosen coin on a randomly chosen pane. We pick the second coin at random. We put it onto the remaining not occupied pane. And by doing so, we fix the choice for the third coin. It automatically sits on the table. And for demonstration purposes, let us agree that the coin that went onto the left pane in this case is named X. The coin that went onto the right pane is named Y. And the coin that sits out this weighing on the table is called Z. From the analysis of a similar, simpler related problem, the two-coin problem, we know the two possible outcomes recorded over here in the previous segment. But this time, because we have three coins, can the panes balance in this case? The answer is yes. The panes can balance when the coins named X and Y are genuine. And then that means that when the panes balance, what do we know with absolute certainty? With absolute certainty, we know the identity of the fake coin. Now we know with absolute certainty that the coin named Z, the coin that was sitting on the table, is the fake one. But we know nothing about its weight quality. It can be heavy or it can be light. And that is how we record our outcome. The coin Z can be heavy and the coin named Z can be light. Now, after the first weighing, we generated the demand for how many units of information? 1, 2, 3, 4, 5, 6. We generated the demand for 6 units of information, which basically reflects the fact that with 3 coins with not known ahead of time weight quality, how many outcomes we have? Well, the coin X can be heavy and light, the coin Y can be heavy and light, and the coin named Z can be heavy and light. 3 times 2 is 6, 6 possible outcomes, and all these outcomes are captured over here at the bottom with the nodes that are at the moment leaf nodes in this tertiary tree. And the question is, can this general 3-coin problem be solved in precisely one way? We know that the answer to this question is a resounding no. In the previous segments, we discovered that with a single weighing on a properly functioning set of fair pen scales, we can generate no more than 3 units of information. 3 is strictly less than 6, so there is absolutely no hope of solving this 3-coin problem in one weighing. There is a hard theoretical barrier for that. It's theoretically impossible. So now we think, in how many weighings can this 3-coin problem be solved? Well, before we answer that question, let us analyze the outcomes a little bit more carefully. What happens, for example, when the panes, in this case X and Y, the panes containing the coins named X and Y, do balance? Well, we already noticed that in that case, we know with absolute certainty the identity of the fake coin, that is Z. But what else does that mean? Well, that means that the coins named X and Y on the panes that balance are no longer suspects. These coins are genuine. Consequently, we promote these coins from being suspects into being genuine coins, and we will agree to refer to all the genuine coins as control coins, and we'll designate them with the letter C. In other words, in this case, we'll depict it symbolically: X equals Y equals C. C for a control coin. Likewise, let's say what happens in the case when the pane that contains the coin named X goes down. In this case, we know that either the coin named X is heavy, fake and heavy, or the coin named Y is fake and light. That automatically means that the coin named Z, with absolute certainty, is a genuine coin, hence it's a control coin. So we know here Z is a control coin. Likewise, when the pane that contains the coin named Y went down, we know that this is the potential distribution of qualities of the fake coins, and that also means that the coin named Z is no longer the suspect. This coin is named C for control or genuine coin, and this is precisely the property of elimination of coins from a suspect pool and the promotion them into the pool of genuine or control coins. And this is the property of the adaptive solutions of fake coin detection problems, to which I referred in the earlier segment. Now, let's say, for example, let's try to attack this guy. When the panes balance as the result of the first weighing, then can this scenario, when the coin Z is either heavy or light, be resolved with absolute certainty in one weighing? Well, the answer to that question is yes. All we have to do here is, for example, put the Z coin on the left pen, put the control coin on the right pen, and perform the weighing number 2. What are the possible outcomes of this weighing? Well, at this point, we know with absolute certainty that the coin named Z is fake. That means that in this case, the panes cannot possibly balance. Consequently, in the weighing number 2 in this path, we can have only only two outcomes, I'm sorry. Either the pane that contains the coin Z goes down, in which case the coin named Z is fake and it is heavy, because only the heavy coin can go down, or in this case, the pane that contains the control coin goes down, but that means that the pane that contains the coin named Z goes up, and that means that the coin named Z is fake and light. Wonderful. So here in 2 weighings we covered this case, and we generated 2 units of information that cover the case with the Z coin. Let us address this case when the coin X is a heavy suspect and the coin named Y is a light suspect. What can we do in this case? Technically, and this is a good point of discussion, we have 2 distinct solutions in this case. We can put the coin named X and heavy, let's say, on the left pen, and weigh it against the control coin, which was the coin Z over here. In this case, what are the possible outcomes of the second weighing? Well, we know that in this case, the pens can actually balance, because if the coin named XH is a genuine one, that means that the fake coin is the coin named Y, and it is light in its weight quality. Can, in this case, the pane that contains the control coin go down? The answer is, of course, no, they cannot, because then the heavy suspect has go up, and that is absurd. That is not possible. So the only possible scenario here is the case when the pane that contains the heavy coin goes down, and that identifies the coin X as a heavy fake coin, as shown over here. And what is the second technically distinct solution? Well, in this case, I will not be erasing this, but you guys understand what's going on. We can weigh the light suspect, YL, against the control coin. And what are the possible outcomes in this case? Well, in this case, the pane that controls the pane that contains the control coin can go down, because in this case, the pane that contains the light suspect Y will go up. And in that case, it means that the fake coin is Y and it is light. And what else is possible over here? Well, the balancing outcome is possible. If the panes balance, meaning that the coin named YL is genuine, then the fake coin is X and it is heavy. So these are 2 technically distinct solutions in this case. Now let us analyze the case when the right pen goes down and our suspects have opposite weight qualities. Again, here we can weigh, for example, the coin named YH heavy against the control point. What are the possible outcomes here? Can the pans balance in this case? The answer is yes, they can. If they do balance, then the fake point is X and it is light. Can the pan that contains the coin YH go up? The answer is no. This suspect is heavy, so if the pans do tip over, they must tip that way. The pan that contains the heavy suspect goes down, YH. And we also realize that due to the symmetry, inherent symmetry between these two cases, we can also, for yet another solution, weigh, for example, XL, the light suspect, against the coin C. Let's say we put it on the right pan like so. In this case, if the pans balance, then the fake coin is Y and it is heavy. And can the pan that contains the coin named XL go down in this case? Of course not, it cannot. Only the pan that contains the control coin can go down. That means that the pan that controls the coin named XL for light suspect will go up. And in this case, the fake coin is X and light. Now let's take a quick look at the outcome of this experiment. How many units of information do we generate, let's say, over this tree right here? Let's count. 1, 2, 3, 4, 5, 6. And if we take any of the other distinct solutions, we'll get the same count. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, and so on. Either way, we account for all 6 possibilities in the 3-coin case, and we see that the general 3-coin problem can be solved in precisely 2 weighings. This will be weighing number 1, and let's say if we designate it like so, and this will be the weighing right here. This, and this will be the weighing number 2. And in real time, those of our viewers who caught on to this procedure will try to carefully solve more and more complicated problems with 4 coins, 5 coins, 6 coins, and so on, until they come up to the original problem of 12 coins. I will skip this analysis for demonstration purposes to keep the length of this episode manageable, and in the next segment we will look at the solution of the original 12-coin proper. As we begin our search for an adaptive solution of the 12-coin problem, we observe that no solution of no worthy mathematical problem pops out of the blue and comes to us in vacuum. And conversely, each solution of any worthy mathematical problem only comes after a personal effort and a personal struggle. Parabolically speaking, if we cross the blades with the pirate, then we have to look the pirate in the eye, because that is the only way we can fight a successful fight, if we understand who our opponent is. In mathematics, that means that the chance, in order for us to have a chance to solve a problem, we need to develop the understanding of what type of problem we're dealing with, and that understanding comes precisely through the solution of various simpler cases of the problem at hand. And that is exactly what we did in the demonstration above, by trying to solve the problems when the number of coins is very small, 1, 2, 3, and so on. Consequently, when we solve these simpler cases, we develop the tactical ideas and insights, and we develop a natural terminology, so that when later on in the solution of the actual difficult to solve problem, we come up with the terms like heavy, light, partition, and so on, this terminology comes naturally. As such, when we approach the solution of the 12-coin problem, we already understand that in that solution, no matter what that solution is, we need to account for how many possible outcomes. Well, we need to account for 12 times 2, 24 possible outcomes. And for example, we can write down this as the following set of outcomes. The coin number 1, let's say, can be both heavy, and the coin number 1 can be light. Then the coin number 2 can be heavy, and the coin number 2 can be light, and so on. The coin number k can be both heavy, coin number k can be light, and so on. And the coin number 12 can be heavy, and the coin number 12 can be light. And this set of options gives us 24 possible outcomes. And in order to accommodate for all these 24 possible outcomes, we need to find a creative, perhaps, way to combine the coins at the same time in the same space. In other words, we need to decide how many coins will go on each pen for each weighing, and overall each weighing will be represented by the coins that sit in different spaces at the same time, as suggested by the space-time problem-solving approach. As we try to solve this fake coin detection problem when the number of coins is, for example, 4, 5, and 6 and higher, then we understand that for the first weighing, we need to decide on the partition of our 12 coins. And by partition of 12 coins, we mean the decision to put that many coins on the left pen, that many coins on the right pen, and keep that many coins on the table. So with all its combinatorial might, so to speak, what choices do we have for our partitions for the first weighing? Well, we can put, for example, one coin on one pen and one coin on the other pen. We'll refer to this partition as 1 plus 1. Then we can do the same for 2 plus 2 manner, when we put 2 coins on one pen and 2 coins on the other. Then we can proceed in the manner 3 plus 3, 4 plus 4, 5 plus 5, and 6 plus 6 partition. So here, let me maybe underscore this, guys, make a little table. Here we reason as follows. Let us analyze these possible candidate partitions for the case when the pens balance and when they do not balance. In other words, in our k plus k partition, let's say here we also will write the value of k just for the sake of the argument. Here we'll have k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6. And we want to analyze the possible outcomes of the very first weighing from the perspective of the amount of information that we will be asked or demanded to compute, and we will need to square or balance that demand against what can possibly be produced with the remaining 2 weighings. So here we'll say the case when the pens tip and when the pens balance. Now let's think about it from the solutions of the previous simply related problems. We know that if we put, for example, let's say k coins on the left pen and k coins on the right pen, then we can have fundamentally basically 2 outcomes with respect to when the pens balance or not. So let's say consider the first case. When the pens do not balance, will symbolize the outcome when the pens do not balance with the not equal sign, and we have k and k coins on each pen. Then what does that mean in terms of the information distribution across the coins and the remaining weighings? If the pens do not balance, then that means that the suspect coin is on one of these panes. And that means that if we do that on all the cases, how many coins do we have on the table? That is correct. We're given 12 coins altogether. So we have 12 minus 2k coins sitting on the table in this partition. And in this case, when after the first weighing, the panes do not balance, that means that we have 2k suspects. We have 2k suspects, and we have 12 minus 2k, just in case, we'll write it down here, control coins. These coins are no longer the suspects. They are eliminated from the pool of suspects, and all these coins that were on the table are the genuine coins, and we refer to these genuine coins as control coins. Now let's think about the demand for the information in this case. If the pens did not balance, it doesn't really matter which pen in this case went up and which pen went down. We know with absolute certainty the weight quality of the corresponding coins. That is, all the coins that are located at the same time, at the same space, or at the pen that went down, they become heavy suspects. And all the coins that sit on the pen that went up, they become the light suspects. Consequently, K heavy suspects plus K light suspects gives us a total amount of 2K suspects. The weight quality of each of which is known ahead of time. Consequently, we will need to produce 2K amount, 2K units of information in order to solve the problem with absolute certainty, and we need to square that amount of the demanded information against what? Well, we're given 3 weighings. We just executed 1, 3 minus 1, 2. So from the previous solutions of the previous simply related problems, we know that we'll need to square this against the theoretically possible 9 units of information that can be extracted from the remaining 2 weighings. In the second case, when the pens, let's say K, do balance, and we have K coins in this case, then what does that mean? Well, that means that each and every coin on the pens that did balance is no longer a suspect. Each such coin is promoted to the genuine coin, or we call this control coins. It means that in this case we have access to 2K control coins. These guys are control coins. And what does it mean? It means that all 12 minus 2K coins that were sitting on the table are the suspects. We will write it down over here. 12 minus 2K are the suspects. Now are the suspects. And in terms of information, how much information do they demand in order to solve this problem with absolute certainty? Well, because these coins that were on the table did not participate in actual weighing, we do not know anything about their weight quality with absolute certainty, and each one of these 12 minus 2K coins can be either light or heavy. That means that each such coin will give us 2 options, and in general we will need to square 2 times 12 minus 2K units of information against the same 3 squared units of information that are theoretically possible from the remaining, that we can acquire from the remaining 2 weighings. Armed with this information, we compile this table, which is very straightforward to do. When the pens tip over here, we simply see that, okay, in the 1 plus 1 partition, we need to generate 2 units of information. When the the 2 units of information, yes, that's correct. When the pens tip over in the 2 plus 2 partition, we need to generate 2 times 2, 4 units of information. When the pens tip over in the 3 plus 3 partition, we need to generate 6 units of information. In the 4 plus 4 partition, 8 units of information. In the 5 plus 5 partition, 10 units of information. And in the 6 plus 6 partition, 12 units of information. Now let's look at how much information do we have to generate when the pans balance. In the case of 1 plus 1 partition, we have what? 12 minus 2, 10. 10 times 2 is 20. So we need to generate 20 units of information. In the 2 plus 2 partition case, how much information do we need to generate? 12 minus 4, 8. 8 times 2 is 16. We need to generate 16 units of information. In the 3 plus 3 partition case, when the pans balance, we need to generate what? 12 minus 6 is 6 times 2, 12. We need to generate 12 units of information. In the 4 plus 4 partition case, we need to generate 12 minus 2 times 4 is 8. 12 minus 8 is 4. 4 times 2 is 8. We need to generate 8 units of information. In the 5 plus 5 partition case, how much information do we need to generate? 12 minus 10, 2. 2 times 2 is 4. We need to generate 4 units of information. And the 6 plus 6 partition case cannot happen with the balancing outcome. This cannot happen because these are all the coins. Precisely one coin here is fake. So in this case, in the case of 6 plus 6 partition, the pans cannot possibly balance. Now we'll look at these two columns over here, and we want to highlight or select only those k plus k partitions which square against our requirement here, 9 units of information that are theoretically possible in either case. For the first partition, we see that yes, 2 is less than 9, but then we have here a whopping demand for 20 units of information. We can only produce 9, so this cannot happen. The 1 plus 1 partition is eliminated. In the 2 plus 2 partition case, we see that yes, 4 is less than 9, but 16 is still greater than 9. This is no good. This partition is eliminated. Now, for the 3 plus 3 partition, what do we see? 6 is less than 9, but 12 is still greater than 9. No good. Eliminated. The 4 plus 4 partition. Here something interesting is going on. 8 units of information needs to be produced when the pans do not balance, and similarly, also 8 units of information needs to be produced when the pans do balance. Either way, 8 is less than 9. This partition is a keeper. We keep this guy. 5 plus 5 partition. 10 is already greater than 9. Eliminated. There is no hope over here. Theoretically impossible. And in a 6 plus 6 partition, also we see that 12 is greater than 9. Not happening. And in some sense, we actually see that the 6 plus 6 partition is perhaps the least useful one, because after we execute the first weighing in the 6 plus 6 partition, we still do not know anything about the identity of the fake coin, but we sort the given coins into two groups. We know that all the coins, all 6 coins that were on the pan that went down are now heavy suspects, and all 6 coins that went up are the 6 light coins. Consequently, from this experiment, we see that the only partition that gives us some theoretical hope is this one, the partition when we put 4 coins on one pan, 4 coins on the other pan, and we keep the remaining 4 coins on the table. And this is our first small victory. We managed to eliminate all the possible partitions, reduce it to only one, 4 plus 4, and we next will design our first weighing. Wonderful. By analyzing all the possible partitions of the 12-coin problem for the first weighing, and by trolling all these partitions through the demands of information that needs to be produced, and comparing these demands against the theoretical possibilities what can be produced, we realize that the only winning combination in this case is the 4+4 partition that I captured over here. Consequently, right now we will design our first weighing, and for that purpose I will not refer to these coins as 1, 2, 3. This is too complicated. We'll keep things simple. We will say that, again, let's say we shake all 12 coins real well. We yank the first 4 coins at random from that pile and we put them on any randomly chosen pane. We excavate another 4 coins again at random from whatever remains in the bag, and we plop them on the remaining pane, and whatever 4 coins were left in the bag after the second excavation, we put them on the table. We will refer to the coins in the first pile as simply, let's say, X, 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 X. We are committing here a notational crime, of course. In the set, all the elements must be distinct, but we understand what's going on. And we measure these coins against the coins named Y, 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 Y. Again, let's say for demonstration purposes, we have the coins that are obviously named in a distinct way. Let's say 1, 2, 3, 4 on the left pane, and the coins that sit on the right pane will be named, for example, 5, 6, 7, 8, and consequently the coins that are named 9, 10, 11, 12 sit on the table. But for demonstration purposes, we will refer to these coins as X coins on the left pane, Y coins on the right pane, and the Z coins on the table. We'll have 4 Z coins on the table. And again, from our previous analysis, we know that when the panes do balance, then we have right away 8 coins that are genuine. These coins are eliminated from the suspect pool. It seems a little bit more straightforward to deal with that many coins. So consequently, we will analyze the first case when on the first weighing, the panes do balance. And we will record symbolically that fact, not with our traditional graph. Don't worry about it. At the end of this episode, I'll show a complete, a sample complete solution with all the weighings laid out. But here, instead of drawing graphs and trees, we'll simply say that right now we'll consider the case when X, 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 and X balances with a Y, Y, Y coins. And then we know right away that all these coins are genuine, and each such coin is promoted to be a control coin. So here we'll say that we have 8 control coins at our disposal, and we have 4 suspects named Z1, Z2, Z3, and Z4, for example. Now, because these coins did not participate in the actual weighing, we do not know anything about the weight quality of these coins, and we know that each such coin can be heavy or light. 4 times 2 is 8. We have a demand to produce 8 units of information, but we know that theoretically we can do no better than 3 squared, 9 units of information. 8 is less than 9, so at least there is a theoretical hope. That is why we proceeded with that specific partition. But now comes the question, how do we design the same time, same space distribution of these 4 coins so that we solve this problem precisely 2 weighings? And here it may seem to be very difficult to come up with a partition that will work. Combinatorially, there are potentially quite many different ways to combine the coins. And for example, when I was solving this problem, I was thinking about the way in which we can circumvent that potentially very large amount of combinatorial work and trying to analyze all the possible cases. And that is where the idea to which I referred in the previous segment as a hint um, was I was able to generate this idea. In other words, my idea was to apply the reverse order problem solving approach to the search for the solution of the distribution of coins for the second weighing. That is, we are told that the author of this problem thinks that this problem can be solved in precisely 3 weighings. Right now we executed, right now over here we executed 1 weighing. The panes did balance. Now we have 2 weighings remaining. The challenge is the tactical challenge from the perspective of combinatorial amount of work that we need to do in order to generate the distribution of points for the second weighing is very large. We want to cut it down, but here applying the reverse order problem solving approach to this problem, we think as follows. If this problem can be solved in 3 weighings, that means that the final and the third weighing must solve this problem completely. And our idea is to see what type of problem is even theoretically possible to be solved in 1 weighing. And if we generate all these possibilities, of which there shouldn't be too many, then we can step back and work our way in reverse order in the direction from the third weighing towards the second weighing, and then we will come up with the second weighing in which the distribution of point is forced to obey or to honor the demands of the final weighing. Consequently, what kind of problems can we solve with precisely 1 weighing? And remember that that weighing, the third one, must solve the problem on this path completely. Well, that is why in some sense we did in the previous segments, we dealt with the smaller and simpler versions of this problem. 1 coin, 2 coin, and 3 coin problems. And from this experience, we know right away that with 1 weighing, we can solve the following problems. When there is 1 coin, we'll name it, well, in this case, we'll call it Z, but let's say without the, we'll call it the Z coin, which we can balance with the control coin. And then without knowing the weight quality of this coin, we can determine whether the fake coin is light or heavy. We know how to solve this problem. Then we can solve the light when we're given 2 light coins. We can solve the heavy problem. We know how to solve this guy. We know how to solve heavy. We know how to solve light problem when 3 coins are given here and here, and their weight quality is known ahead of time. Here is a 2 coin problem when we know their weight quality ahead of time. And what are the remaining situations? Well, the remaining problems that we can solve with 1 weighing is heavy, light, and its conjugate, light, heavy. Also, based on these specific strings, they depict the groupings of coins, and we can see here that we can introduce the term of conjugate groupings or conjugate strings. And for example, 2 strings could be called conjugate or conjugate images of each other if one such string can be obtained from the other mechanically by replacing all the letters in that string. For example, if we're given the string HH, we can obtain its conjugate image by replacing uniformly all the letters H with the letters L, and we obtain, for example, this grouping, and conversely. Or let's say for demonstration purposes, take this grouping right here, LLH. In this grouping, we replace the first L with the letter H, the second L with the letter H, and the letter H here with L, and we obtain this string right here, and conversely. And if we undertake the analysis of the possible situations in a similar way in which we analyze the outcomes when we were solving simple problems, then we will see that in the case when the pans balance on the first weighing and we have 4 suspects of unknown weight quality, then the cases with LL and HH are simply impossible, and we left fundamentally with HHH, these two guys, these two conjugate images, and these two guys over here. Fundamentally, these two groupings, or these two types of distributions of coins over the pans for the last weighing, is what dictates the two distinct solutions for the second weighing after the pans balanced on the first weighing. And how do we design these weighings, for example? Well, in this case, it's quite straightforward. Let's say we'll try to design the second weighing based on the fact that we know how to solve this type of problem on the final and third weighing. Well, that is straightforward. Let's say we name one coin Z1, for example. Let's say Z1, and we put the coin named Z2 on the left pan. We weigh these two coins against the remaining coin named Z3. We put the control coin to balance these guys out, and we keep the coin named Z4 on the table. You see how straightforward this design for the second weighing. Let's say if this is the first weighing and this is the outcome of this weighing, then this will be the weighing number 2. Why this design was straightforward? Well, look, what are the possible outcomes over here? Well, let's say the left pan, the pan that contains the coins named Z1 and Z2, which we made unique by assigning them the traditional indexes, went down over here. Then what? What does that mean? What does that mean in this case? Well, in this case, it means that the coins Z1 and Z2 became what type of suspects? Heavy suspects. So we have Z1 heavy, we have Z2 heavy, and what else do we have? We have the coin named Z3 light. Z3 is light. And can we solve, this will be the weighing right here, this will be the weighing number 3 at this point. Can we solve this problem when this outcome takes place? Obviously, we can solve this problem just by looking at these conjugate strings. In this case, we just have to weigh two coins of the same quality against each other, H against H and L against L. And if the pans balance, then the remaining coin is it. And the pen that goes down in the HH case points to the fake and heavy, and the pen that went up, in this case, LL case, points to the coin that is fake and light. That is all there is to it. So here, which way we execute the third weighing? Well, it's straightforward. Here we execute Z1, which is heavy, against Z2, which is heavy. And what are the possible outcomes over here? Can the pans balance in this case? Yeah, sure. If both coins Z1 and Z2 are genuine, then the only outcome here possible is that the coin Z3 is fake and it is light. And in this case, if the pen that contains the coin Z1 went down, what does that mean? It goes down right here. Well, the fake coin is Z1 and it is heavy. Z1 and it is heavy. And if the pen with the coin named Z2H went down, what does that mean? Well, that means that the fake coin is named Z2 and it is heavy. Problem solved. If the pens in this case do balance, and can they balance? Yes, they can, because still we have a suspect over here. Well, in this case, we have one suspect. About the weight quality of which we know nothing, but that covers this case. One coin weighed again against a control coin solves the problem in precisely one weighing. So here, when we analyze this case, we know that, for example, let's write it down, the coins Z1, Z2, Z3 are all control coins. They're all genuine when the pens balance. The identity of the fake coin now is known with absolute certainty. It's the coin Z4, and we just have to nail the weight quality of that coin. And how do we do it? Well, we measure, or we weight the coin named Z4 against any of the control coins, of which we have plenty right now. We have 3 control coins here, plus 8 over here. So we have 11 control coins at this point, plenty to choose from. And what are the possible outcomes? Well, it can go either way over here. The balance outcome in this case is not possible because we know with absolute certainty that Z4 is the fake coin. So either the pane that contains the coin Z4 goes down, in which case the coin named Z4 is fake and it is heavy, or the pane that contains the control coin goes down, which means that the pane that contains the Z4 coin goes up, and that means that the coin named Z4 is fake and it is light. Problem solved again. Let us analyze the final case. What happens if the right pen over here, the pen that contains the coins Z3 and C, goes down? Well, we have the conjugate case over here. 2 coins light, 1 coin heavy. Look at that. Z3 went down, it's heavy, or these 2 guys went up, they are light. So now what do we have? Z1 light, Z2 light, Z3 heavy. And how do we solve this problem? Well, we know how to solve this problem. We simply weigh the suspects that have the same weight quality against each other. Game over. So we put, for example, the coin Z1 light on the left pen. We put the coin Z2 light on the right pen. What are the possible outcomes over here? Well, if this pens balance, then the coin Z3 is fake and it is heavy, right? If these 2 coins are genuine, then the only choice is the coin Z3. It is fake and heavy. We know that with absolute certainty. If this pen, the pen that contains the coin named Z1L, went down, it means this guy, Z2 is fake and light, right? Because only the light coin can go up under normal gravity conditions. And if the right pen, the pen that contains the coin Z2L, went down, it means that the other pen, the pen that contains the coin Z1L, went up, and the coin named Z1 light is fake and light. Now let us count how many outcomes did we generate with this solution. Z1, Z2, Z3, which actually corresponds to this pair of conjugate groupings. 1, 2, 3, 4, 5, 6, 7, 8. We generated 8 outcomes, precisely the number of outcomes that is possible in this case when we have 4 coins with an unknown weight quality. And just to make sure that we did not goof off anywhere, let's fix the coin, for example, Z1. Z1 heavy, Z1 light, check. Z3 light, Z3 heavy, check. What about this guy? Z2 heavy, Z2 light, check. And we have nicely these 2 guys in the middle, Z4 heavy and Z4 light, which accommodates for all the possible scenarios when 4 coins of unknown weight quality are given. And this is it for the pair of conjugate strings shown over here, HHL and LLH. In the next segment, let's analyze this situation when we have 2 different conjugate strings, HHH and LLL. Now let us design the second weighing that is based on the conjugate template HHH and LLL. Again, how can this be done? This can be done in a straightforward manner as well. If we do the following, we take the 3 coins, we name them Z1, Z2, and Z3. We square them against 3 control coins, C, C, C. We keep the remaining coin Z4 on the table, like so. And why is it legal? Well, remember that in this case, when the panes did balance on the first weighing, we have access to how many genuine or to how many control coins. Precisely, we have 8. 8 is greater than 3. We can definitely grab 3 control coins. We have them. It's all legal. It's all good. And this is what we do. And again, this should be more than straightforward and more than transparent, because again, let's say in this case, what are the possible outcomes? Well, let's say the left pan, the pan that contains the coins Z1, Z2, Z3, went down. What does that mean? Well, that precisely means that all the coins Z, I'll write it down here, 1, 2, 3, are heavy suspects, and we have precisely the HHH case. In the third and final weighing, we will be fighting the fight with this guy right here, and we know how to fight this fight. Are we so clever that we just guessed it? No, as we explained before, we use the reverse order problem-solving approach, and we realize that on the third weighing, this is the problem that we can solve. Working our way in reverse, we design the second weighing, or the weighing that forces the outcome to be what we already know how to deal with. And when we have 3 heavy suspects, we already dealt with this problem in the segment where we were solving the 3 coin problem with the known ahead of time weight quality. And what do we do here? Well, we have different options. By the looks of it, we can do what? Z1, Z2, Z1, Z3, Z2, Z3, but let's keep it simple. On the third weighing, we will square the coin named Z1 heavy against the coin named, let's say, Z2 heavy. And what is possible over here? Can the pens balance? Yes, they can. In this case, if they balance, then the coin named Z3 will be fake and heavy. If the left pen that contains the coin Z1 went down, then Z1 is fake and heavy. And if the right pen went down, it means that the coin named Z2 is fake and heavy. That much should be straightforward to understand. This is all wonderful. If the pens balance, and can they balance? Yes, they can, because we still have the sneaky little coin over here named Z4 sitting quietly on the table. And if that happens, then we already have it from the previous segment. We know how to fight that fight. 1 coin, the Z versus C scenario. We weigh the coin named Z4 against the control coin C. We know that the balancing act over here is impossible. With absolute certainty on this path, this coin is fake, and there are only 2 options here. When the pan that contains the coin named Z4 goes down, then the coin Z4 is fake and heavy. And if the pan that contains the control coin goes down, that means that the pen that controls the coin named Z4 goes up. This guy is fake. 4 is fake and light. And let us also analyze the case when the pan that contains the 3 control coins went down. What does that mean? Well, that means that under normal gravity, under normal conditions, we have 3 suspects over here, and all these suspects, because they went up, they're what? They're light. Wonderful. So we write it down. Z sub 1, 2, 3. They are all, will superscript light. The coins named Z1 to 3, they are light suspects right here. And what do? Again, we measure, for example, the coin named Z1 light versus the coin named Z2 light. If they balance, then Z3 is fake and light, right? If the pens balance, that means that the coins Z1, Z2 are genuine. The only choice is the coin Z3. We know its identity at this point with absolute certainty, and it's light. If the left pen goes down here, or the pen that contains the coin named Z1 light, then the other guy is it. Then the coin named Z2 is fake and light. And if the pen that contains the coin Z2 light goes down, it means that the pen that contains the coin Z1 light went up. This guy is it, Z1 light. And this is our second distinct solution based on the HHH-LLL conjugate pair. Let's count the number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8. The numbers look good. What about the individual coins? Z1 heavy, Z1 light, check. Z2 light, Z2 heavy, check. Z3 heavy and light, check. And again, the coin Z4 in the middle, both heavy and light, covers all the cases, and this solves the problem of the case when the pens do balance on the first weighing, and these are the second and the third weighings. But make no mistakes, the straightforwardness or the perceived straightforwardness of the design of our two possible weighings over here came at the effort, or perhaps some sort of lucky idea, to use the reverse order problem solving approach and to cut down significantly the amount of combinatorial work for that path of this problem. And in order to show you, for example, that, again, I will not be doing it here in its completeness. I want to keep the duration of this segment manageable so people have the stamina to watch it. But what will remain outside of this video, for example? Well, let's say we think that this conjugate pair right here, LLL and AH is a candidate. What happens then? Well, let's quickly do it right here. Let's say we weigh the coins Z1, Z2 versus Z3 and Z4. These two coins right here, Z1, Z2 on the left pen, let's say, and Z3 and Z4 on the right pen, thinking that this conjugate pair may provide us another distinct solution. Well, what are the possible outcomes here? We know that the fake coin must be here. It cannot be anywhere else. So there is no balance. There is no balancing act, not happening. So the pens will tip either this way or that way. But regardless of which way they go, what can we say? Well, in this case, for example, when the pen that contains the coin named Z1, Z2 goes down, what do we have? The coins Z1, 2 are heavy, and the coins named Z3, 4 are light. How many outcomes is this? 4. And in the other case, here, the coins Z3, 4 are heavy suspects, and the coins named Z1, 2 are light suspects. Again, how many cases? 4. This particular weighing, as number 2 in this case, generates the demands for 4 units of information. Can we produce 4 units of information on the final third weighing? No, we cannot. We already know that. I lost this formula here, but let me write it down over here, just maybe here. Remember the 3 to the kth power, right? The amount of information that we can produce with one weighing cannot be better than 3 units. 4 is greater than 3. No go. This is not happening. And in a similar way, the other cases can be shown to be simply impossible. Thus, on the path when the pens balance on the first weighing, shown here, and in this case, when we have 4 coins of unknown weight quality, we have 2 distinct solutions, which are driven by these 2 conjugate templates, and we can even call them that way. Or, for example, the second solution was, which one? Z1, Z2 versus Z3 and C. These are two distinct solutions of the path when, after the first weighing, the pens did balance. And in the next segment, we'll take on quite exciting, but admittedly a little bit more intimidating case when the pens, as the result of the first weighing, did not balance, and we have to fight the fight with what? We have to produce another type of 8 units of information. In the previous segment, we saw how a fairly clever idea of using the reverse order problem-solving approach to solving the problem completely worked beautifully for us. And here, when as a result of the first weighing, the pans do not balance, the situation is essentially the same, even though, yes, it sounds a little bit more intimidating because instead of 4 coins, we have to deal with 8 coins. But let us look at what is really going on. Let us assume for demonstration purposes that the X coins went up as shown with the blue arrow over here, and the Y coins went down as shown with the arrow over here, and the case when the event of balancing the pans goes the other way. In other words, when the coins X go down and when the Y coins go up, is analyzed in exactly the same way due to the symmetry of the situation that we observed earlier, and it can be done by uniformly replacing the letters X with the letters Y in the solution that we will unfold right now. Now, if the pans, as the result of the first weighing, did not balance and the Y coins went down and the X coins went up, what does it mean first? First, it means that all the coins that were on the table are no longer the suspects, and that means that all the Z coins are eliminated from the suspect pool. They're promoted into the genuine coins, and we refer to genuine coins as control coins. We designate them with the uppercase letter C, and that means that in this case, the Z coins become the 4 control coins, and as we shall see very soon, we will need all of them. We also know with absolute certainty the weight quality of all the X coins. All these X coins now become the light suspects as designated with the letter L over here, X1L, X2L, and so on. And likewise, with absolute certainty, we know the weight quality of all the Y coins because these coins went down. They are now promoted into the heavy suspects as shown with the uppercase letter H over here, Y1H, Y2H, and so on. And even though, yes, we have to deal with 8 coins compared to the 4 coins that we dealt with in the previous case when the pans balance on the first weighing, we see that from our previous analysis of K plus K partitions, we remember that information-wise, amazingly enough, these two cases are the same because either way we have to produce 8 units of information and in 2 weighings. That is, because we already executed the first weighing, 3 minus 1, 2. So now we have 2 weighings to solve the problem completely. And here comes the reverse order problem-solving approach idea. Yes, combinatorially, the amount of work that we may have to do in order to try to design the second weighing in case of 8 coins can be very large. And in some sense, we cannot really control it. But what we can control in a good sense are the problems that can be solved with precisely one weighing, and that is the idea of using the reverse order problem solving approach here. The third and final weighing must allegedly solve this problem completely, even in this case. And we know precisely which problems can be solved with one weighing. These problems are listed over here. This idea plus the next one. Remember that right now we're studying the mechanics of the space-time problem-solving approach, and one of the pairings in the space-time problem-solving approach is same time, same space. And if we keep that pairing front and center in this situation, what tactically useful idea can we generate? Well, let's think about it. If as a result of the second weighing the pans balance, then whatever coins were left on the table are the coins that must be solved, so to speak, during the third and final weighing. And how much information can we produce with one weighing on pen scales? We cannot do better than 3 units of information. Consequently, we cannot afford to have more than 3 coins that will sit on the table during the second weighing. That means that at all times during the second weighing, we have to have at least 5 coins, 5 suspect coins, distributed over the pens, which is another way of saying that the number of coins that do not participate explicitly in the weighing on the pens during the second weighing cannot be more than 3. Keeping these ideas in mind and the idea of the reverse order problem solving approach, we work backwards and we try to design the second weighing in this case in such a way that the possible outcomes of that second weighing honor the demands precisely of the problems that we can solve with one weighing. And yes, it's fairly tedious work in real time to somehow convince yourself that you have found all the possible solutions. But over here on your right, for your convenience, I listed all 13 distinct solutions of the 12-coin problem in the case when, as a result of the first weighing, the pens did not balance. And what do I call a solution? Well, a solution is a distribution of coins across 2 pens which allow the problem to be solved completely and with absolute certainty as demanded and recover the 2 requested units of information. Also, for your convenience, I listed these solutions in the decreasing order of the number of coins per pen. 5 coins, 4 coins, and then 4 coins up to here, and 3 coins starting from here, 3, 3, and 3. Also, for your convenience, I have grouped these solutions as conjugate pairs. Here are 2 distinct 5 coins per solution. Here, here, and here we have 4 coins per, and starting from here, 3 coins per, 3 coins per, 3 coins per. And of somewhat special attention over here is the solution number 5, because that solution is its own conjugate, which means that if in that solution we replace uniformly the letters H with the letters L, we still have 2 letters L. Letters L with H, they become letters 2 letters H again. And here we simply swap these guys, but essentially this is one and the same solution. In a public setting, together with you guys, I will analyze one case from each grouping, and the cases that I will not analyze, you should be able to analyze and construct the solution tree for these cases on your own without any problems. Here I will do, for example, this one, the top solution over here, the template, 3 heavy suspects, 2 light suspects on the left pen, and 1 heavy suspect on the right pen. And the translation from this generic notation to specific ones should be transparent. Basically, we give specific names to the heavy coins, such as, for example, Y1, Y2, Y3. These are the heavy suspect, H, H, H. And we give the specific names to the light suspects over here. For example, we take the first 2 X, the light X suspects over here. We put the remaining heavy suspect on the right pen, and we balance all this beautiful mess with 4 control coins. Why we can do it? Well, we can do it because precisely we have 4 control coins that were formerly known as the Z coins that were on the table during the first weighing. And it turns out, again, we need all 4 coins in this case. It follows that the 2 light suspects, X3 light and X4 light, are sitting on the table as shown over here. Let us, in an expedient fashion, analyze the possible solution in this case. If the left pen over here goes down, we'll show it over here, then what are the possibilities for the distribution of coins here? If the left pen with 3 heavy suspects went down, that means that the right pen with the 1 heavy suspect went up. Under normal gravity, can a heavy suspect go up? No, it cannot. So this guy is gone. Can, under normal gravity, the 2 light suspects go down? No, they cannot. So what are the only options if the left pen goes down? Well, the only option here is that the three heavy suspects are it. We need to find, we know with absolute certainty the weight quality of this suspect, but we do not know the identity. But in the previously solved problem where, remember, we went through this beautiful reduction process, we already know how to do it. And for example, we can measure, let's say, coin named Y heavy 1 versus the coin named Y heavy 2. If the pans balance, then the fake coin named Y3 and it is heavy. If the left pen goes down, then the fake coin is Y1 and it is heavy. And if the right pen goes down, then the fake coin is named Y2 and it is heavy. Can the pans balance in this case? Yes, they can, because we have two light suspects on the table. And again, here we have, I'll write it right like this. Here we have a couple of choices. We can, for example, weigh one light suspect again against one of the how many 10 control coins that we have, or we can weigh these coins against each other. I'll go for the latter case for symmetry. So here we weigh the coins X light 3 versus, let's say, X light 4. Can the pens balance in this case? No, they cannot, because one of these coins is fake with absolute certainty. So if the left pen goes down, then it's the other coin, X3 is fake and it is light. And if the right pen goes down, then the fake coin is X3 and it is, I'm sorry, this is 4. 4, this is 3 and light. So this is X4, X3. Now let's analyze the case when the right pen goes down. What can happen over here? If the right pen containing the one heavy suspect went down, that means that the left pen that contains three heavy suspects went up. Under normal gravity, can the heavy coins go up? No, they cannot. So these guys are eliminated. So that means that the two light coins, one of them can go up, or one heavy coin can go down. So here again we see that in the first case, when the left pen went down, we have our HHH template, and when the right pen goes down, what do we have? Light, light, heavy. This is precisely this guy, light, light, heavy. See how beautiful this solution unfolds if we are lucky enough to generate this clever out-of-the-box idea of solving this problem in reverse order. So in this case, we measure the coins of the same quality against each other. For example, we go X1 light versus X2 light. If the pens balance, then the fake coin called Y4 and it is heavy. If the left pen goes down, then the coin named X2 is fake and light. And if the right pen goes down, then the left pen goes up. The fake coin is named X1 and it is light. This is it for the analysis. Let's carefully count the number of outcomes that we generated. 1, 2, 3, 4, 5, 6, 7, 8. All 8 cases are accounted for. And again, just to make sure that we did not go forth, let's count the light candidates. X4, check. 3, light, check. X4, light. X2, light, check. And X1, light. So all 4 light candidates are, or 4 light suspects are accounted for. Now let's deal with the heavy suspects. Heavy 1, heavy 2, heavy 3, heavy 4. Beautiful, problem solved. And in the next segment, I will analyze the case when the 4 coins are placed on one pen. In the previous segment, we completely analyzed the solution number 1 shown on your right, and in this segment, we will completely analyze the solution number 3 shown over here. And while the first solution contained 5 coins per pen, this solution will contain 4 coins per pen, and you can do the remaining 4 coins per pen solutions on your own. And number 3 and number 4 over here are conjugate solutions. In other words, if we find one, we automatically find the other, so it's not as intimidating as shown over here for the total number of 13. And in this weighing, again, it's very transparent to see how we go from a generic template to a specific one. We basically give specific names to the heavy suspects, and we give the specific name to the light suspects. Here we have 2 heavy suspects, Y1 and Y2, 2 light suspects, X1 and X2. We have 1 heavy suspect on the right pen, balanced with 3 control coins that we have over here. We have 4 of those, but in this experiment we use only 3. And that means that in addition to the previous case of having the light coins 3 and 4 on the table, here we also have the heavy suspect coin number 4 on the table as well, for a total of 3 coins. And again, this is the maximum we can afford for this problem. Let us see what happens in this case if the left pen that contains the 2 heavy and 2 light suspects goes down, and that would imply that the right pen that contains the sole heavy suspect goes up. Under normal gravity, can the heavy suspect go up? No, it cannot. So this coin is out. Under normal gravity, can the 2 light suspects go down? No, they cannot. So these 2 coins are eliminated. So we only have to deal with 2 coins. We already know how to solve this problem from the previously solved problem. Remember our beautiful reduce and conquer, or the process of reduction of problems, making them simpler. So here we have Y coin number 1 heavy. We weigh it against the coin number 2 Y heavy. Also do realize that this is our second weighing. Will be weighing number 2, and this will be over here weighing number 3. So in 3 weighings we solve the problem completely. What can happen over here? In this case, the pens cannot possibly balance. We know that fake coin is one of these. So if the left pen goes down, then the fake and heavy coin is named Y1. And if the right pen goes down, then the fake and heavy coin is named Y2, as shown over here. If the pens balance, then we have what? By the looks of it, we have 9 control coins, and we have 3 suspects over here, 2 light, 1 heavy. This is precisely this beautiful template over here, light, light, heavy. And in this case, we had what? Heavy, heavy. It is, by the looks of it, this guy, heavy, heavy. So in the light, light, heavy, heavy case, light, light, heavy case, what do we have? We measure, for the third weighing, we measure the coin named X3 light versus the coin named X4 light. If the pens balance, then the fake coin is named Y4 and it is heavy. If the left pen goes down, then the fake coin is named X4 and it is light. And if the right pen goes down, then the fake coin is X3 and it is light. And in the final case, when the right pen that contains the sole heavy suspect goes down, that means that the pen that has the 2 heavy and 2 light suspect goes up. Can under normal gravity heavy suspects go up? No, they cannot. The only suspects are here. And again, we come down to which generic template, courtesy of the reverse order problem solving approach? Light, light, heavy. And there it is, light, light, heavy. And in a sense, we just witnessed how we design the second weighings over here, precisely by working with what can possibly work on the third weighing shown over here, here, and here. And in this case, we basically measure weigh 2 competing coins of the same weight quality. So here we will measure X1 light versus X2 light. When the pens balance, then the fake coin is named Y3 and it is heavy. When the left pen goes down, the fake coin is X2 and it is light. And when the right pen goes down, then the fake coin is x1 and it is light. Let us now carefully compute the number of outcomes that we have covered. 1, 2, 3, 4, 5, 6, 7, 8. By numbers we're good, but now let's look at the heavy suspects. Heavy 1, heavy 2, heavy 3, and heavy 4. Check for the heavy suspects, and now let's do the light suspects. Light 1, light 2, light 3, and light 4. All the outcomes are accounted for. This is another distinct complete solution, and in the next segment I'll pick one of these 3 coins per scenarios and analyze their solution completely with you. For our last complete analysis in the public setting of a distinct solution of the 12 coin problem when the pans do not balance on the first weighing, I'll consider light, light, heavy, light, light, heavy, or this number 13, the solution number 13. And again, the reason I'm doing is because I want to show that it's not this analysis is not really that complicated. If I were doing this with the live audience, I would literally take the demands from the audience at random. Let's say you give me any of the scenarios and I will analyze it right then and there for you. It's not that complicated once you understand the beat and the flow of how these things work, especially if you came on your own to the idea of using the reverse order problem solving approach and unwind the design of the distribution of coins for the second weighing that way. Here again, we translate a generic template into the specific coin names by assigning specific names to the generic names. 2 lights on the left and 2 lights on the right become x1, 2, x3, 4, and the heavy suspects become y1, y2. That also means that the 2 coins that will sit out this particular weighing will be the 2 heavy suspects, 3 and 4. Again, we know the weight quality of these coins with absolute certainty. We don't know which one, and that is precisely, again, the creative juice, so to speak, of the reverse order problem solving approach as it comes in, dovetails into the search for a solution of this problem. So here, let's analyze the case when the left pen that contains the 2 light suspects x1, 2, and 1 heavy suspect y1 goes down. What does that mean? That means that the pan that contains the remaining 2 light suspects and the second heavy suspect goes up. Can the heavy suspect go up under normal gravity? No, it cannot. So this guy is out. Can likewise the light suspects in normal gravity go down? No, they cannot. So these 2 guys are out. So in this case, when the left pen goes down, we have what? We have 2 light suspects, again, squaring against the heavy suspects. Again, this is our light LLH template, which is one of the only ones that's solvable in one weighing in the final experiment. So here we again measure the 2 competing coins with the same weight quality. That is, we measure the coin named x3L against the coin named x4L. When the pans balance, then the fake coin is named y1 and it is heavy. When the left pen goes down, then the right pen goes up. So the fake coin is named x4 and it is light. If the right pen goes down, then the fake coin is named x3 and it is light. Very well. If the pans balance, then the only 2 suspects are the heavy coins 3 and 4. Again, we know how to solve this. In some sense, we have two distinct types of solutions. We can measure one of the coins against the control, or we can measure them against each other for symmetry purposes. Let's say we measure them against each other. Y3 heavy versus Y4 heavy. They cannot possibly balance. If the left pen goes down, then the fake coin is named Y3 and it is heavy. If the right pen goes down, then the fake coin is named Y4 and it is heavy. And we actually have symmetrical case when the right pane goes down, except that here analysis is quite similar. If the pane on the right goes down, then the fake suspects that are light, they cannot go down. So here we have the suspect Y2 heavy. Likewise over here, when the left pane that contains the heavy suspect Y1 went up, the fake heavy suspect cannot go up. So we have the competition between two lights X1, X2 versus the heavy suspect Y2. Again, we measure these two guys against each other. So we measure X1 light versus X2 light. When they balance, then the fake coin is named Y2 and it is heavy, Y2 and it is heavy. When the left pane goes up, it is this guy that is fake and it is light, X2. When the right pane goes down, then the fake coin is named X1 and it is light. Game over. Let us carefully count the number of outcomes that we generated in this solution. 1, 2, 3, 4, 5, 6, 7, 8. And again, how many light suspects do we have? X4, check. X3, check. X2, check. X1, check. All the light candidates are taken care of. What about the heavy ones? Y1 heavy, Y2 heavy, and 3 and 4 heavy. And this is it. This is a complete solution of this case. It has its own conjugate right here, number 12. And the remaining cases, you guys should, it's a good idea to analyze on your own. But again, do not try to make a copy of my solutions over here. Try to understand how the solutions were produced, and then you should be able to generate the solutions on your own. And over here, I'll show one complete solution with the coins named 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right here. And in conclusion, it should now be evident and clear why I have titled this episode Not Blind Mathematical Justice, because in the solution of the 12 coin problem that we generated in this episode, that solution was adaptive, and that means that in each consequent weighing, we adapt the distribution of coins over the panes and over the table depending on the outcome of the preceding weighing. And overall, the process of some sort of brute combinatorial enumeration and elimination sometimes leaves a little bit of a bad taste in the mouth, because we're still not sure that, yes, we generated 13 distinct solutions for the case when the panes do not balance after the first weighing, and we showed in one of the previous segments the 2 distinct solutions when the panes do balance, and we're still not entirely convinced that this is it. Maybe there are 14 or 15, maybe we missed some distinct solution in either case, and that situation, that level of uncertainty in a way, and ironically enough, can be addressed with a grown-up notion of mathematical entropy or information entropy. This final segment of this episode is optional. It's for curious travelers only. Feel free to skip it and go to the next challenge. But here we will discuss briefly how the notion of mathematical entropy or information entropy, not to be confused with the entropy that we use in theoretical physics, can be applied to the process of searching for a solution of certain problems. In a lightning round, the historical background here is the following. The American Ralph Hartley in 1928 suggested that if a particular experiment, say named alpha, has a number of outcomes, A1, A2, and so on, AN, then the level of uncertainty about a specific outcome can be measured with the logarithmic functions. If that experiment can have k different outcomes, then the measure of uncertainty about the outcome of the specific outcome of this event can be measured with the logarithm of k. And later on, 20 years after the introduction of the notion of logarithm of k by Hartley, another American guy named Claude Shannon suggested that this uncertainty measured in terms of logarithms is not very precise. It can be improved, and he introduced basically the notion of what we now refer to as information entropy. The formula shown over here, it looks a little bit scary, but it's not that scary. It basically has the net minus sign in front of it because the probability of each outcome over here captured with p of a k, the probability ranges between 0 and 1. The value of the logarithm, as we remember, is negative over here. So when we multiply probabilities by the logarithm of probability, that comes out to a negative. We compensate it with the negative sign over here, and it turns out that in some situations this average level of uncertainty about the outcome of a specific experiment, where several outcomes are possible, is captured precisely by this formula. And in our case, as it pertains to the 12-coin problem, the notion of probability, which I designate with the p over here, p of probability of the outcome a sub k, can be understood in a pretty elementary, proverbial middle school level as a rational number, where in the numerator we put the total number of favorable outcomes, and in the denominator we keep the total number of all possible outcomes, and that is our probability. So how does the notion of information entropy can help us over here and put all our combinatorial work over here on a solid theoretical footing? Well, the idea here is the following. The design of the notion of mathematical or information entropy, if you once you begin studying it and you think about it for some time, you will realize that the highest or the maximal amount of information can be extracted from an event that is associated with the highest value of entropy. In other words, when the outcome is the most uncertain, then we derive the most information from it. So that's the basic, fundamental, essential idea. And the details here go as follows. Let's say in the first case, recall our k coins on the one pane and then k coins on the first pane. Recall the segment where we analyzed the design, the potential design, and the partitions of the coins for the very first weighings. If, for example, let's say if the panes in this case, for example, balance, if they balance, then what does that mean? That means that the coins that are on the table, and we have precisely 12 minus 2k such coins sitting on the table, then one of the coins, the fake coin, is one amongst those. And the number of possibilities for these coins is what? 2 times that number, because each coin can be light and heavy. So the probability that this specific coin with this specific weight quality will be fake, will be given by what? Well, 2 times 12 minus 2k over what? This is total number of favorable outcomes divided by, in the middle school fashion, divided by what? By the total number of outcomes. That's 24. And once we cancel, by the looks of it, what? 4s, then we have 6 minus k over 6, where k, let's say, varies over 1 through 6. This is the probability of the event when the pens balance. When the pens do not balance, so if, for example, k coins on one pen do not balance with the k coins on the other pen, then what is going on? Here we want to capture two possible outcomes or two experiments. Let's say the left pane going down, and the other experiment, the right pane goes down. If the left pane goes down, then one of the coins on the pane that went down is heavy candidate, and one of the coins in the pane that went up is the light candidate. What is the total number of favorable events? K plus k is 2k. And what is the total number of all possible events? 24. So there we go, 24. Cancel the 2's. K over 12 is the probability that one of the uh, coins on the panes is it. If, let's say, the left pane goes down, and if the right pane goes down, well, it's actually the situation exactly the same. If the right pane goes down, then one of the right coins, so to speak, is heavy, and one of the left coins is, so to speak, light. Then again, k plus k is 2k. That's the number of favorable outcomes over total number of outcomes, 24. So k over 12. And there you go. We have three experiments. The left pane goes down with this probability. The right pane goes down with the probability of the coin on the panes being it given here. And when the panes balance with the probability of the coin being on the table given here, we have three experiments. We construct three expressions for the information entropy by this specific formula, and we again do elementary, nothing more than rational number computations in the proverbial middle school style. We come up with three numbers, and we pick the one with the highest entropy. And it so happens that, let's do this together fairly expediently without spending too much time on it. We already know what's going on. K equals 4. When k equals 4, let's write it down over here. K equals 4. 6 minus 4, 2. 2 over 6, 1/3. And then that's the probability of the coin being fake on the table. And then k 4 over 12, also 1/3 in either case. So 1/3, 1/3, 1/3. And it turns out that with the apparatus of mathematical real analysis, let's say, it can be shown that this specific function over here, I'll write it like down, x times log x, basically reaches its maximum when all these weights, so to speak, these guys x over here are one and the same. And if we think about it, then equiprobable events generate the highest entropy. In other words, it's the most difficult way to predict these events when they all have equal probability. So again, we come back to the partition of points 4 plus 4 plus 4 as a solid theoretical proof with elementary computations. Bingo, that's the solution that we also picked, but we picked it based on a different approach of analyzing, in some sense, doing deep dive, doing a deep or greedy depth first analysis, if you will, all the way down. We had to analyze what can be and what cannot be done. Here with elementary computations, we prove that yes, the 4 plus 4 partition is the only one when we bring in the notion of information entropy, and the remaining cases over here can also be analyzed in a similar fashion by again computing the probabilities carefully. And once we know the probability, we know how to compute logarithms. This is all smooth sailing after that. So just about the only challenge here is to carefully compute the probabilities of different events under different partitions. This is it for the solution of the problem S2M4, and next we will look at the next challenge or mathematics problem S2M15. Our next challenge will be the mathematical problem S2M15, and the challenge in this problem will be very much related to the problem that we solved in this episode. So if you want to take on the problem S2M15, that you should really spend your time and understand what unfolded in this episode. But in the problem S2M15, we'll be given 18 points. We will know the weight quality of the fake coin ahead of time. Let's say the fake coin is heavy or fake coin weighs detectably more than genuine coins. And in 3 weighings, the challenge is to determine with absolute certainty the identity of the fake coins as we know its weight quality. But the real challenge here is to come up with a non-adaptive solution, for the 18 coin problem. In this episode, for the 12 coin problem, we designed together and developed an adaptive solution of the fake coin detection problem, in which we very much cared about and we looked at each outcome of the weighing in this problem, and we reacted to or adapted to the result of this weighing by affecting the distribution of coins for the next weighing. In the problem S2E15, the challenge is not to come up with an adaptive solution, but with a non-adaptive solution, which you can write on a piece of paper, give it to someone else, that someone else will walk into a different room where you cannot see that person. That person will follow the recipe, follow the instructions of your non-adaptive solution, come back, give you the piece of paper with the results. You will look at it and you'll say, with absolute certainty, this is the fake coin and it's heavy. And as you understand now, precisely because we looked at the result of each weighing in our adaptive solution, that is why the title of this episode is not Blind Mathematical Justice, precisely because we look at each outcome of each weighing. But in the problem S2E15, the challenge is to design a non-adaptive solution. And as you might have guessed already, the title of the next episode will be Blind Mathematical Justice. And now we realize that the ancient Greeks, who came up with the idea of a young lady who is blindfolded holding a set of pen scales, what they were actually after, they did not care about justice, but they were solving the fake coin detection math problems back at the time. Okay, that was a joke. It is important to have a healthy sense of humor if you are doing mathematics, and you should not take yourself too seriously. But on a serious note, if you think that you cannot solve the problem S2E15 with 18 coins, amazingly enough, try to solve it with, let's say, 27 coins. And if you catch on the whiff of what's going on, you'll realize that a 27 coin solution is 27 coin problem in this case is somewhat simpler and more straightforward to do. Anyway, this is it for this episode. Thank you for your time. Thank you for watching. I will see you in the next episode, S2E13, where I will discuss the solution of the mathematics problem S2M15.